Hello, good day everybody. Be welcome to RealCosmic Math, where math makes the thought fly. Today's topic is one that so many times are not so reviewed with enough detail, at least according to my own experience, and nevertheless is convenient to know. It's much commended that integrals allow to obtain the amount of area under the curve of a function. But how do they actually do it, and why do they actually do it? If you're interested, I would like to invite you to know why do integrals calculate the area under the curve. In order we comprehend this, at first let's imagine the graphic of a function. Underneath the line of the function, there is an area. This area is irregular. Historically, the calculation of irregular areas is one of the most studied problems by mathematicians. Since ancient Greek, Archimedes came up with the idea that we could obtain an approach to the amount of area in an irregular surface if we stack rectangles inside of it, and then we add up the areas of each one of them. But by doing that, we don't contemplate the area of the small hollows which the rectangles can cover. Likewise, other alternative is to fill the area with rectangles above the line of the function, but while rectangles under the line don't cover the hollows, the rectangles above the line have remainders upon the area. Despite of it, it's also true that the smaller the rectangles are, the better they fit inside the area, and the better their heights will approach to the neighboring point of the function's line. That is increasingly accurate for smaller and narrower rectangles. In fact, they should be so narrow that they turn into lines. They would be so small to make the rectangles cover the whole area. We say that because in fact, when the rectangles are narrower, and as a consequence its base has less length, it looks more like a line. Then, if the base has no length, we can ensure that the rectangle is actually a line. Now, by putting our attention back to the graph, let's draw a rectangle under the line of a function. The area of this rectangle is approximately equals to the area under the curve. The rectangle has a base with any length value. We will call this value as h. Meanwhile, we can notice that its height goes from the x-axis to a rectangle's corner that is over a point that is in the graphic of a function. That point has coordinates x, f of x. Each point of a function's graphic indicates the values that takes f of x according to the x values. If f of x represents the vertical coordinate of any point, then the rectangle has a height with a length that is equals to f of x. Thus, the area of this rectangle is h multiplied by f of x. By calculating this area, we obtain an approximation to the area under the curve. If our goal is to calculate the exact area under the curve, we have to do something different. In that case, we have to look for a function that allows to calculate the exact area under the curve of the function f of x. We call a of x to that function. But we still don't know how is the expression of the function, namely if the function f of x is equals to x squared or x plus 3 or anything else. We don't know it yet. Well, even when we don't know the function, we can describe a little bit how this works. The nature of a function is that when we enter a value, it makes a process with the incoming datum, and then returns another value. The function a of x previously mentioned works like that. Once we set a value for x, a of x will return the value of the chunk of area under the curve that is between 0 and the value set for x. For example, if the income value for x is 5, when evaluating in the function a of x, it will return the value of the area from 0 to 5. Now, if that is the way our function works, then it means we are not able to calculate directly the area from 5 to 7, from 9 to 13, from 8 to 17, because the function always returns the area's value from 0 to any other value of x, always starting from 0, not from another number. If we wanted to calculate an area under the curve that doesn't start from 0, at first we have to obtain the area from 0 to the limit of the right side of our area under the curve to calculate. We will call this area as area 2. On the other hand, the area from 0 to the limit of the left side of our surface under the curve will be the area 1. If we subtract the area 1 from the area 2, we'll achieve to get the area of our interest. Now, if we take a rectangle that had an area almost equals to the area under the curve again, and considering the area of that rectangle is h multiplied by f of x, and the area of the surface under the curve was an area 2 minus an area 1, Then we deduct that f of x is approximately equal to the subtraction of a of x plus h, namely our area 2 minus a of x, our area 1. We generate this expression. If we take the full expression and divide it by the value of the base h in both sides of the equality, we get the heights of the two areas. This is due to in every rectangle, the area is equals to the base multiplied by the height, and therefore the height is equals to the area divided by the base. And as we did here, we divided both areas by the base h. Dividing all the expression by h is a strategy to get f of x isolated in the left side from the rest of the expression. It's easy to understand the exact area of the rectangle as the multiplication of h by f of x. However, when we try to do the same thing for the height of the area under the curve, it could be confusing because at first glance it seems like this area has two heights, but actually the height of the expression we got for the area under the curve actually means to an only value. In order to grasp the idea of that height I am talking about, let's imagine the area under the curve as if it were clay we can mold however we want. If we mold the area under the curve with the shape of a rectangle but without widening it, that is, without modifying the basis length of our area under the curve, well, once we have this rectangle, we measure its height. The value we obtain is just the height of the area under the curve. As we realized before, the smaller the rectangles, the better they cover the area under the curve, and they'll do it totally if their bases measure 0, because that way there won't be hollows, they will be exactly equal. If we want to transport this idea to mathematical language and retake the expression we got, we want to make the base h equals to 0. But as you know, divisions by 0 cause mathematical problems, so we have to use the mathematical tool known as limit that allows us to make h equal to 0, but avoiding the mathematical issues when dividing something by 0. We apply the limit when h is approached to 0, of course in both sides of the expression, in order to maintain the equality. Now we solve the limits. In the left side limit when h approaches to 0 of f of x, having nothing in terms of h, it stays the same. We put the equality sign because, as we've seen before, when the base h measures 0, the height of the area of the rectangle and the height of the area under the curve are not approximately equal but just equal. To solve the right side, we must apply the definition of derivative, limit when h approaches to 0 of f of x plus h minus f of x all divided by h. Above the box with the definition is happening the same thing, but instead f of x we have a of x. We apply the definition of derivative and the expression looks like that. We're using the notation of derivative, which I have shown in the box using an apostrophe upon the letter of the function as we see in the screen. Therefore, the function we were looking for the value of its area under the curve is equal to the derivative of the area's function a of x. So, if we want to obtain a of x, we must remove the derivative. In other words, we have to integrate. Finally, we just have understood the reason why the area's function of any other function is the integral of this one, but something is left. Why the defined integral is calculated the way it is. As I explained before, if we evaluate x in our area's function, the result was the value of the area from 0 to x. To troubleshooting this issue, we can apply the strategy we've talked before. We call the value of x, which delimits from the left side the area we want to calculate as a, and the value of x, which delimits from the right side, will be known as b. If we calculate the area up to b and we subtract the area up to a to it, we obtain the area of our interest. Bringing this logic to the defined integral from a to b is equal to the area up to b minus the area up to a. Formally expressed in mathematical language, the area under the curve is equal to the antiderivative evaluated in b minus the antiderivative evaluated in a. And that's how we demonstrate how the defined integral is calculated the way it is. And that's all, mates. If you like the video, you can support me by sharing it with your friends and people that probably may be interested in learning this kind of content related with math. Thanks for watching.